ducks in a row here. All right, so let me check. Shuvik, I do have your submission on Gradescope. Awesome. Yeah, if you want me to check, I can do that. All right, so quiz number 1. Done. Oh, that's a weird smiley face, isn't it? Whee. Oh, I almost forgot. I have these fun stickers. Well, maybe we'll do well done. Cute. All right, so let's see. Section 1.5 is on inverse functions and logs. We won't do any review because we did exponential functions, and they were sort of a little bit on the quiz, but they'll come up later, so I'm not too worried about them. Okay, so inverse functions. A function has an inverse if it's 1-to-1, meaning each input of x can only yield one output of y. So a function, or I'll say only functions that are 1-to-1 have inverses. Okay. So from our notes, I'm going to grab the definition of 1-to-1 so we can see what it means to be 1-to-1. And then we can talk about it. So a function f is called 1-to-1 if it never takes on the same value twice, meaning so the output at x1 can't be equal to x2 if x1 is not equal to x2. So what that means is each input, or rather, I'll use a different color here. Each unique input of x must yield a unique output of y. Okay. Now we can check this. The easiest way to check it if a function is 1-to-1 is graphically, but I'll also show you how to use this definition in order to check it mathematically or algebraically. So there are 2 ways. There's probably more ways, but 2 common ways, I should say, but I won't change it. So there are 2 ways to check if a function is 1-to-1. The first one is graphically, so you use the graph. Graphically, use the horizontal line test. And I'll bring in the little blurb from the horizontal line test here. Copy. Oops. But really all it's saying is the horizontal line test says that, okay, if no horizontal line, so remember horizontal is straight across like this, if it doesn't intersect the graph more than once, then it's 1-to-1. So just as a kind of a quick example, if you have maybe, let's say, an exponential function, maybe it's like this, right? If you use horizontal lines here at any point, right, you're only going to intersect this graph once, meaning it's 1 to 1. Versus if you have kind of our common parabola, maybe, right, something like that. Well, not a very beautiful parabola, but that's okay, right? It doesn't actually matter which point, right? There are two values of x that give the same output, whereas 1 to 1 by definition says that, okay, each unique input of x, in this case, let's think about -2 and +2 squared, right? They both give you 4, and so you're not getting a unique output. So this is not 1 to 1. Okay. Meaning it's not going to have an inverse. It's still a function, right? So we've got the vertical line test, which is checking for a function, versus the horizontal line test, which is checking for 1 to 1, which in the end, right, if it's 1 to 1, it has an inverse, right? So let's see here. The other option, right, for checking to see if a function is 1 to 1, so graphically is a nice, easy way you can use a horizontal line test. The other way is to check it mathematically. Now, the ones I give you will be kind of easy. There are some that are a little bit harder. So sometimes doing it kind of algebraically, let's call it algebraically, right? Mathematically, it's all math, right? So algebraically sounds better. But algebra is just addition, subtraction, it's just math. So algebraically, what we do is we take this definition, right? The output at x1 can't equal the output of x2 if x1 is not equal to x2. So how we translate this into something that we can work with is, instead of x1 and x2, I actually like to use a and b. And so what we do is, to show that a function is 1 to 1, or maybe to show that it's not 1 to 1, what we do is set f of a equal to f of b. Then simplify. And if you find that a equals b, f of x is 1 to 1, right? If the output at a is equal to the output of b, then what you should find is that a is equal to b, right? The input of these two are actually the same. If you don't, then it's not 1 to 1. Okay? And we'll do an example in a little bit, but I want to introduce all the inverse stuff first. Okay, so this is what we'll use a lot of the time if you have to prove something, is 1 to 1. So let's see here. What's kind of fun about the inverse, you might remember from different math courses, but the inverse is denoted by a -1 in the power. You have to be really careful, right? Because -1 usually means that you put it in the denominator, but when it's on the function, it's the inverse function. So B. So if the function is 1 to 1, and if the function has a domain of a and a range of b, and we're going to use that just in a little bit here, then the inverse function f to the -1 has domain B and range A. Okay, so that's kind of cool. So usually it's easier to find the domain than to find the range, right? Sometimes graphically it's easy to see what the range is, but to kind of calculate what the range is can be tricky. So what's nice is if you're able to find the inverse function, then you're able to find the domain of the inverse function, right? Finding the domain is usually, you know, pretty okay. What inputs can I put in here, right? So finding the domain of the inverse is a way that you can find the range of the original function, but also the range is the same of the inverse is the same as the domain of the original function. So they cross over, right? And so here, what I want to highlight sometimes it is easier to find the range of f by finding its inverse, assuming it's 1-to-1, and finding the domain. Of the inverse, I should say. One thing that I do want to note here, right, it's really important that you differentiate between f of negative, so the inverse function of x is not the same as f of x to the -1, right? F of x to the -1, this is equal, this would mean 1 over f of x, right? Which is not the inverse function. This is the inverse function notation, right? So that's really important. And just, I've got this little summary piece here, right? So the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. So you can use those to find the domain and range of both. So what does it mean to have an inverse? Well, the inverse takes essentially an old output and gives you the input, right? And so it's working backwards. Usually we put in a value of x and we get the value of y, but the inverse works the other way. I give it a value of y and it tells me the value of x. So you can see the problem. If it doesn't give you unique values of x, then it doesn't know what to do, right? So that's why you have to land on a unique value of x. Just as a rule, okay. As a rule, and I'll paste this thing in here, the inverse composed with, right? This is the same as the composition formulas that we were just dealing with, right? The inverse composed with the original function should cancel out to x, right? And then the function composed with the inverse should also reduce to x, right? So what we can do is we can use these properties to confirm that the inverse we found is in fact the inverse. So maybe I'll move this here a little bit bigger. We can use these function compositions to confirm the inverse we found is indeed the inverse of f. Okay. So how do we find the inverse? And this, should be review from before. So finding the inverse, there's kind of two ways that you can do it. They are the same, but I've outlined, I stole the outline of one of the ways that you can do it. And just to not be confusing, I'll stick to this one. I'll try to stick to this one. So to find the inverse of a function, okay, your first step is going to be, so you've got a function f of x that you need to find the inverse of. So you're going to write y equals that function. Okay? And then instead of solving for y, because you already have y equals something in terms of x, okay, what you're going to do is you're going to solve this for x in terms of y, right? So you're going to slowly solve for x. And then what you're going to do is you're going to interchange x and y, and the resulting function is the inverse function. Okay? The other way to do it is to up here swap your x's and y's immediately, right? Instead of waiting to swap them and then solving for y like we usually do. It doesn't matter, right? We're just doing things in different order. But as long as you stick to one method, it's fine. Okay, so these problems cover a lot of ground, right? Because typically what I'll get you to do is I'll give you a function, right? And then I'll ask you to prove that it's one-to-one, right? It will be one-to-one if I ask you to prove it. So you know you should be showing that A equals B. So what do? We go back here. And so to prove that it's one-to-one, right, you would set f of A equal to f of B and then simplify it until you have A equals B, right? And then you can conclude that it's one-to-one. Then what I get you to do is I get you to find the inverse, right? And so to find the inverse, you go through these steps here, right? Solve for x in terms of y and then swap them, and then you've got the inverse. And then what I get you to do is I get you to confirm that what you found was the inverse by using these properties, right? So you use these function compositions. So you take the inverse composed with the function, and it should simplify to x. And then you take the function composed with the inverse, and it should simplify to x. You should do both of these, right? Even though it seems a little bit redundant. Usually I just do them kind of side by side. Okay. So we've got example 4, but I'm going to add to it just to show you what I want you to do here. Kind of a typical. So A, show f of x is one-to-one. Okay. You've got options. If you draw the graph, then you could use the horizontal line test, right? I'm going to specify algebraically here, but you can confirm it by drawing it in Desmos and just making sure that it passes the horizontal line test, right, which it will. This is where it comes in handy from, I can't remember what section, 1.2 maybe? When we reminded ourselves about the shapes of these things, right? X to the power of 3 plus 2 is just going to be x to the power of 3 moved up 2 units. X to the power of 3, remember, looks something like that, right? Which in our minds, we can kind of say, okay, well, it looks like it would pass the horizontal line test, even if I shift this up 2 units, which I've done here, right? And so we suspect that it will be one-to-one, and that's what we're going to show. Then find the inverse of f of x. Then show maybe I should say confirm the inverse. I can't remember, does it call them the cancellation properties? No, they don't. Confirm the inverse using the function compositions. Okay. So, all right. So first thing we're going to do is we've got this function f of x, x to the power of 3 plus 2. So we already, by knowing what it kind of looks like, we know it's going to be one-to-one. So things are going to work out, right? So here in part A, what I'm going to do is to show that it's one-to-one, I do f of A is equal to f of B. So I force them to be equal to each other. Okay. Which means I'm using A as an input and then B is equal to an input. And I know it looks stupid, but sometimes it actually doesn't work out. So A to the power of 3 plus 2, if it's equal to B to the power of 3 plus 2, does A equal B? Okay, so what you're going to do is you're just going to cancel things out, simplify until hopefully you end up at A equals B. So here we've got, I'm going to move A to the 3 plus 2 minus 2 is B to the 3. Just kind of showing every step, you don't have to, right? And so now I'm at A to the power of 3 equals B to the power of 3. What's nice about powers of 3 is that it retains negatives. You have to be careful with even powers. And if you think about even powers in general, right, have this parabolic shape, which we know automatically won't pass the horizontal line test, right? And so, and the reason for that is because the square doesn't retain the negative, right? Whereas a power of 3 or an odd power in general will retain the negative. And so when I take the third root of both sides here, trying to get rid of either one of these powers of 3, right? If I take the third root of A to the power of 3 is equal to B, right? Say I took the third root of B, well, I take the third root of A to the power of 3. Maybe I'll just show the same thing here. Because the third root retains the negative, I land at A is equal to B. So therefore, so now you always want to back it up with a statement, right? So here we were able to show, that if I force f of A to be equal to f of B, so the output at A equal to f of the output at B, then I have to conclude that A must be the same as B. So then in words, you should do a little like summary. So therefore, f of x is 1-to-1. Okay. Good. So because it's 1-to-1, it will have an inverse. So I'll just kind of add that here. The function has an inverse, right? Or it's invertible. So then the second thing I want you to do is find the inverse. Okay, so B, find the inverse. So using those steps that were outlined, and you don't have to break it up in steps. If you just want to do it, that's fine. But what I'm going to do is I'm going to have y equals f of x. So I'm going to follow those steps just so you can see what they look like. So y equals x to the power of 3 plus 2. Okay. So now in my second step, let me just solve this equation for x in terms of y, right? Sometimes it's not possible, but it has to be a one-to-one function, so it will be possible. So now if I'm solving for x, right, I'm slowly going to move things over and slowly shift x to the left-hand side. So I get y minus 2 is x to the power of 3. And then what's nice about the third root is anything goes into it, so that's fine. And like we said earlier, it retains that negative. So when I solve for x here by taking the third root of both sides, what I'm going to do is I'm going to shift this so that the x is on the left-hand side. So I get x is the third root of y minus 2. Okay. So now I've solved for x in terms of y. Okay. The third step, okay, so let it catch up here. To express the inverse as a function of x, now you have to switch your x's and y's, and then what you have is y is the inverse function. Right, so in step 3 here, right, here I'm going to swap your x's with y's, and y's become x's. So then y equals the third root of x minus 2. And here, this y is now the inverse of f. F inverse of x is the third root of x minus 2. Okay. So that's how you find the inverse. The last thing I want you to do is confirm that this is the inverse using those function compositions. And so to do that, right, I need to show that the inverse composed with the original function simplifies to x, and that the original function composed with the inverse also simplifies to x. Right? So part C here. Show that f inverse of x, and I'm going to bring them both here so I can have them kind of available, is in fact the inverse of f of x, which, just as a reminder, is x to the power of 3 plus 2. Okay, so what we do is, like I said, I like to split my page up because usually I can fit both calculations side by side, and then it just is nice to have it in the same region. Doesn't matter. But what we're going to show is that f inverse of f of x is going to be, all right, so here, this is the function, sorry, this is the inverse function composed with the function. Right? And then on the other hand, we're going to show that f composed with the inverse, which is f of f inverse of x, does it equal x? Right, and here, oh, I guess I want to know if it equals x. Switched up my colors, oh well. So the inverse function composed with the original function, I'm going to rewrite the inverse. So I've got the third root of f of x minus 2. Okay. which is going to be, once I substitute in f of x, x to the power of 3 plus 2, and then minus 2, okay, you can see that it's pretty quickly going to cancel out, right? So the plus 2 minus 2 goes away. So I have the third root of x to the 3, which is x. Now, if you do the same thing where you take the original function composed with the inverse, you're going to have f inverse of x plus 2, which is going to be the third root of x oh, sorry. I missed the power of 3. That'll help. And I'll need to move this over a little bit. There. So the inverse to the power of 3 plus 2 is the third root of x minus 2 to the power of 3 plus 2, which is going to be x minus 2 plus 2, which is just going to be x. So what I can conclude here is, therefore, f inverse of x equal to the third root of x minus 2 is in fact the inverse of f of x equals x to the 3 plus 2. So pretty big question that we can develop out of all this, but it's just drawing on things that we already know, right? So function compositions and finding the inverse and proving that it's one-to-one algebraically. All right. Before we end, I'm just going to throw in the fact that graphically, the inverse, and to me, I always kind of have a hard time visualizing this, but the graph of the inverse, you get it by reflecting across the diagonal. So what we're going to see, kind of the most obvious thing, is the exponential function, so e to the x. The inverse of e to the x is the log, which looks like this. So that's what we'll see later on. But we can check it graphically, but to me, it's actually kind of hard to do. So I'm not going to emphasize that, but because if it's hard for me, then it's probably hard for you too. But if you're able to see a reflection across the diagonal, then you have the graph of the inverse. All right. So I think that's a good place to stop today. We're not going to get into logs, but definitely read those notes that I posted on those logarithmic functions. But then we'll talk about those on Wednesday, I guess. Nice work today. And any questions before I let you go for the weekend? Maybe you have other classes, I don't know.
I can't think of any at the moment.
Awesome. Then we'll end there. How about have a good weekend. See you on Wednesday.
You too.
Bye now.